Historically, instrument flying forced a strict geometric limitation on pilots. You had to physically overfly ground-based radio beacons. These transmitters dictated the invisible highways in the sky, known as Victor Airways, tethering aircraft to concrete stations on the ground. Because you could only navigate from one fixed transmitter to the next, flights rarely traveled in a straight line. Instead, pilots flew circuitous, dogleg routes, zigzagging across the country to stay within range of the next physical antenna. Area navigation, or RNAV, solves this geographic problem with onboard processing. It untethers the aircraft from those physical transmitters. The system allows pilots to fly from their departure point straight to their destination, navigating from waypoint to waypoint. It achieves this by electronically relocating those physical ground stations to anywhere in the sky. By treating the flight path as a series of coordinates rather than a sequence of radio towers, RNAV shifts the primary reference for navigation from the ground to the cockpit computer. This is the FAA approach chart for the Lufkin VOR/DME RNAV Runway 7 approach in Texas. It demonstrates exactly how to navigate an aircraft down to the runway without physical beacons underneath the flight path. Looking at the upper left notes, this approach relies on secondary waypoints derived from a single parent facility, the physical Lufkin vortex. Scanning down, we find the initial approach fix, Bovin. The box defines its exact position using specific decimal latitude and longitude coordinates. In a traditional instrument approach, a fix like this would correspond to a physical transmitter on the ground. If you looked out the window at the exact location of Bovin, you would see nothing but empty Texas landscape. To execute this path, the aircraft's avionics must actively conjure a beacon out of thin air. The pilot navigates by trusting an invisible, algorithmic projection. So how does the aircraft physically navigate to Bovin when the actual radio beacon emitting the signal is miles away at the Lufkin vortex? The process begins with the aircraft's NavCom receiver. It remains tuned to the actual physical parent vortex station, in this case, Lufkin. The onboard course line computer takes that raw radio signal and electronically adds a specific mathematical vector to it. By combining a selected radial and a physical distance, the computer projects a point outward from the station. This vector addition transforms that empty space into a pseudo-vortex, an offset virtual radio station, placed exactly at the desired waypoint, Bovin. Provided the aircraft stays within the reception range of the physical parent signal, this calculation can be repeated indefinitely. The computer continually draws new vectors, establishing the next phantom waypoint, like Avado, further down the approach path. Through basic trigonometric vectoring, the navigation system replaces millions of dollars of physical concrete and steel infrastructure with a few lines of onboard geometric processing. Transitioning from physical beacon homing to phantom waypoint navigation requires a shift in how pilots read their primary flight instruments. In the traditional VOR system, the course deviation indicator, or CDI, displays angular deviation. The radio waves spread out from the station in a V shape. This creates an inherent funneling effect. As the aircraft gets closer to the transmitting station, the geometric lines pinch tightly together. A standard 2-degree needle deflection near the station represents a much smaller physical distance than it does 30 miles out, making the instrument hypersensitive. The RNAV tracking logic behaves differently. An RNAV CDI displays cross-track error. This is a constant, linear lateral deviation measured in physical nautical miles rather than degrees. The boundaries run perfectly parallel to the flight path, meaning there is no funneling effect regardless of how close you are to the waypoint. The sensitivity scale for RNAV cross-track error is fixed by the phase of flight. During the en route phase, a 1-dot deviation on the gauge equals exactly 1 nautical mile off course. During an approach, that sensitivity tightens to just 0.25 nautical miles per dot. Because the physical instrument gauge looks identical in both modes, an explicit operational hazard exists in the cockpit. Pilots have historically followed traditional VOR angular information when they mistakenly believed they were reading linear RNAV cross-track data. Misinterpreting this geometry causes the pilot to miscalculate their actual distance from the course centerline. If you apply a standard VOR correction to an RNAV needle, you are making steering decisions based on a scale that doesn't exist. Modern RNAV systems are not limited to calculating two-dimensional lateral paths. They introduce the third dimension to the cockpit through vertical navigation, or VNAV. This profile view at the bottom of the Lufkin chart shows how VNAV operates during an approach. It computes a specific rate of descent relative to the aircraft's ground speed between two waypoints, generating a smooth 3.14-degree flight path angle from Boven down toward Avado. The system translates this mathematical calculation directly onto the cockpit's glide slope indicator. For the pilot, the instruments provide vertical guidance that closely mimics a traditional precision ILS approach. But there is a critical technical caveat. Despite generating precise mathematical vertical guidance, an RNAV approach legally remains a non-precision approach. The VNAV glide path is strictly advisory. Pilots must arrest their descent at the minimum descent altitude figures listed in the category table, regardless of the virtual glide slope. The RNAV computer provides the illusion of a perfect, mathematically guided tunnel straight to the runway. But regulatory safety limits, designed around obstacle clearance, remain the hard deck reality. As the aircraft descends along this final segment, it eventually reaches the Avado waypoint, which serves as the missed approach point. You know you've arrived the exact moment the white 2 flag on the navigation gauge suddenly snaps to from. There is a mechanical finality to this indicator. The exact second that flag flips, the waypoint has been crossed. The operational rule is absolute. If the runway environment is not clearly in sight at that exact moment, the pilot must immediately commence the missed approach procedure and climb away from the ground. By taking unbending radio waves broadcast from a fixed point on the ground and filtering them through onboard vector mathematics, an aircraft generates a perfectly predictable, customized coordinate system.